And then start sharing screen. We will start a new topic, okay? For this one, so today the topic is about ensemble learning. So previously, all we learned is just some single learning approach. But basically, the ensemble is not totally new, because if you recall when we discussed decision tree, and then we learn random forest. Basically, random forest is one of the kind of like concept for ensemble learning. Okay, ensembles means you have multiple approaches together to work together. Okay, but let's see, how do we let them work together? So here is to combine different models for ensemble learning. Okay, and the reason for the need to do the ensemble learning is because of the cause of error. Okay, and we already know that noise can cause error, and the bias and the variance previously we also learned that, and we also learned the trade-off between bias and a variance. For bias, is the model needed to be, not too simple, is it? Because if you get it too complicated, it can introduce a high variance. So how do we find the balance between bias and variance? So we discuss multiple ways, okay? And but like over here, the cause for error can be like noise or bias and variance, is it? As I said, ensemble can help to minimize those factors. So previously, what we learned, bias and variance, is we add more features like for bias, is it? And also your model more complicated, that can also kind of avoid the bias, is it? And for variances, we can also like increase the training data set. But with more complicated model, and if we add more feature, too much more feature, that can also cause a high variances. So high variances spread out too much. It is too spread out versus not too spread out. So that's a very, and the previous we discussed those techniques, and also for variance, we also discuss regularization. And generally speaking, when we discuss regularization, we mean is to tuning. Be careful, okay, about hyperparameter. Basically, so far, what we learned is that C and the gamma, is it? And the gamma is for kernel, okay, a trick. And because for parameters, there are another kind of parameter, general parameter, like weight. So anyway, we already learned quite a number of approaches to discuss about improving model performance. Okay, so what today we will learn are some other, from different perspectives, different angles. We can also do ensemble, because all we discussed previously is regarding single model. Okay, so today we will see ensemble, how can we achieve that? Okay, so the ensemble learning is that the idea is to constructing a set of classifiers. It's not just a single one, okay? And they can have some better predictive performance than any of the individual ones. Okay, so so you're going to use a set of, but if you use a set of, how are we going to combine the different prediction results? So there are a couple of approaches. One is based on, we call it majority voting concept. Okay, majority voting. Majority voting is regarding binary classification. And for multi classification, then it's plurality. Okay, plurality voting. So this is kind of like plurality voting is kind of like our president elections, that not just from Democratic and Republican, but of course majority, major big party are those, but we also have some other small parties in it. So that's on the candidate name. It's beyond the two president candidate names. So that's about multi classification. Okay, and the second approach we will discuss is called bagging. Okay, bagging, the complete name is bootstrap aggregating. Aggregating. Okay, so we take a B and AGG and ING, so that's we call it bagging. So bagging, the idea is try to reduce overfitting. Is that by drawing random combinations of the training set. But here we will see it says with repetition. So the training set, you have the training set, you take a part of the training set out, but you repeat, you may have some repetition. So you may have some samples taken out from the set, but repeat them. Okay, so that's the concept about bagging. Then the third one we will see is called boosting. Okay, boosting concept is to reinforce weak learners. To enforce weak learners. So add more weights to weak learners and retrain them, okay, from their mistakes. Okay, so those are general three category of approaches to do ensemble learning. Okay, and then here it says simple ensemble techniques. When we discuss ensemble learning, sometimes we see this a lot. We say take the mode of the result. So here's a concept called mode. So mode, it is from some statistical term. Okay, it refers to most frequently occurring number found in a set of numbers. Okay, so that's what we call it mode. So basically, the majority voting, okay, like what we previously see, etc. So we take the majority voting as the final prediction. Okay, and sometimes you can also take average, not use the majority, take average of the prediction from all models, and then use it to make the final prediction. Okay, so that's the second approach you can take. The third one is we can also take a weighted average. So you add weights to the average, that it's not purely average. Okay, so you give some weights. Okay, so that's regarding simple ensemble techniques, and we will. So the learning with ensemble, is it, and previously I already said. So the most popular ensemble is majority voting. Okay, but majority voting is for binary classification. Okay, for multi-class, we use a plurality, okay, voting. So this is about after you take a set of classifiers, then how are you going to take the prediction? Is it? So in this diagram, the idea is more clear. Okay, so this we be careful. Okay, over here, this is a complete training set. Complete training set. So you apply the complete training set to different classification models. So maybe this one is a logistic regression. Maybe this one you use SVM. Maybe this one you use perceptron. So you use different classifiers that to do training. Okay, and then with the new data coming in, is it then you have prediction. Is it? So each one has their own prediction. Is it? And regarding the result, then you take the vote, take the majority vote. Okay, suppose this one predict 1, this one predict 1, and this one predict 0, this one also predict 1. So you have like 3 of 1, maybe 1 of 0, then majority is 1. So I say, okay, this going to be the predicted result is 1. So that's a concept about the majority voting. Okay, but over here, we use different classifiers. So this is regarding the ensemble learning, okay, with the majority voting. And the second approach, previously we just had called bagging, okay. So bagging is, it's also ensemble learning, is it? And pretty close related to majority voting, okay, majority voting. So here we also have training set, but if you take a look, the training set each time for different classify, it's their own training set. Okay, so like previously I said, this is the original training set. Then you take, so take a part of it, but with replacement of some samples. So some samples you take, you may repeat twice or 3 times. So basically in the original, maybe you just have that single sample 1 times, and then in this T1, it may occur 3 times, 4 times, 5 times. Okay, so you take a portion, but you have duplicates of some of the samples. Then for each of that, then you apply different classifier. So the remaining parts, the same as the previous one. Okay, it's just regarding the training samples. So we do some manually kind of, you kind of manually add some samples. Okay, but those samples are still from the original data set. Okay, so this is called bootstrap. Okay, aggregation, aggregating. So bootstrap aggregating. So we call it bagging. So bootstrap aggregating is on the training set. Okay, training data set. You're going to do some modification, not completely the original one. Okay, so this is a concept about bagging. So here we can take a look. So over here it shows the samples indices, okay, index. So first one, second one, third one is the indices. And so here is bagging round 1. Is it maybe that for T1? Is it? So you can see T1, it has to repeat a couple of times. Is it? And for all of the others, they just from the original. But because of this, then like some of the samples will not appear in this round. Is it? And then for this case, it's, then we take a look, is it? So 1, you repeat, is it? And 7, you repeat, is it? But then like those 3 not showing in the second training set, is it? So for each different classifier, you use not the same training data set, you use a different one, is it? But with some of the samples are duplicates, okay? So that's called the bootstrap aggregating, okay? So we call it bagging. So that's this concept. Okay, what is the third one we learn is called the boosting. Okay, so what boosting, the major concept is, in boosting is that the ensemble consists of very simple base classifier. So it has some base classifier, okay. Those base, we refer them called weak learners. And normally those weak learners, they just have some slight performance advantage over random guessing, okay, random guessing. And it's as a typical example, weak learning is as a decision tree stump. Okay, so that's kind of one of the examples, is it? Okay, and then, so the concept behind the boost, I'm sorry, I needed to get, okay, so the concept behind the boosting is to focus on training samples that are hard to classify. Okay, very hard to classify. And then to let weak learners learn from misclassified training samples to improve the performance of the ensemble. Okay, so that's the idea about boosting. Okay, so let's see. So here to give a basic idea about the procedures for boosting, okay, for boosting. So what the idea is, like you first draw some random subset of the training samples. Okay, and over here it's without replacement. Okay, without replacement. And then we train a weak learner. Suppose we call it C1. Okay, and then you draw second random training subset. Okay, still without replacement. So this is different from bagging. Bagging, you have replacement, is it? And but here is, that's why we call it boosting, the key point. Then you add 50% of samples, but not just random sample 50%. That must be previously misclassified. Okay, then to train the weak learner. Okay, we call it. So this time you add from the previously misclassified. And then for the next one, what we will do is find the training sample D3. Okay, and for this D3, how it is constructed is for the previous 2 rounds, that they don't agree with each other, then you train. So that's why we said we call it boosting, is it you specifically retrain those misclassified samples. Okay, and then we combine the weak learners, B C1, C2, C3, as a via majority voting. Okay, so this is the basic concept about boosting. Okay, and because of this, is it you're going to retrain the misclassified samples. So for boosting, definitely it can decrease in bias. And of course, the variance is compared with bagging. But on the other hand, it can also be tended to lead to high variance. So boosting, we will use as ADA boosting. Okay, so that's the downside and the upside part. Okay, and over here it says ADA boosting. So how ADA boosting works? Okay, ADA boosting, it's not going to work like what we previously described for the boosting. ADA boosting going to use the complete training set to train weak learners. But when you use complete training set to train the weak learners, and here we will add weights. So here we have some weights, okay, for each iteration. Then you're going to re-weight it in each iteration, okay, to build a strong classifier. So this weight means the samples. So you will add some weights to the samples, okay, and you still use a complete training set, but you're going to adjust the weights. So for misclassify, you're going to add more weights. For correctly trained samples, then you can decrease its weights. So this is called ADA boosting. Okay, so adaptive. So ADA means adaptive. Okay, boosting. Okay. So this is for boosting. So that's the basic concept, okay, regarding ensemble learning. So what next one? Let's take a look the examples. Okay. Find the example. Yes. Okay. The first example is regarding the wine. Okay. So let's see. So here's some diagram to show the concept. So for majority voting, is it, so it's binary, and when you have multi-class, is it, then it's a plurality voting. Okay. And this one we already discussed for majority voting, the concept. Okay. And those parts we can skip that in our example. So for this example, so this example is from the chapter 07. Okay, so chapter 7's example. So this previous part, we can skip that. Okay, and we can start from here. So over here in this example, what it provides, it's provide the hard, so the home crafted majority voting classifier. Okay, and in sklearn, later on we will also see sklearn also has some similar majority voting model we can directly use. Okay, so here it's the author crafted this majority voting classifier. Okay, and over here, so That's why it import those packages. So we are not going to discuss in detail about this majority voting classifier. Okay, so if you know how to use it, then that will be fine. Okay, so we will take a look how to use it. Okay, so it's just mimic the general prediction model, that learning model. So you have the fit, then you have predict, and we also have predict probability, because that's going to be used for the prediction probability. That's used if you record the ROC that and the AUC. Okay, so those help us for the model performance. So model performance is not just accuracy and the confusion matrix, is it? ROC and AUC can also help. It's regarding the true positive rate and the false positive rate, is it? The ratio, okay? And this is area under the curve, is it? And we can also use to help us understand the performance. Okay, and this getter parameter will give you regarding each classifier's parameter information. Then you can see which one you need to do more tuning of it. Okay, so then let's see. In this example, so this one we will use the iris data set, and previously we already saw quite a number of times about the iris, and we will not take the complete set. We will take starting from the 50. Okay, and over here the first one is the label encoder. If you recall, this is for categorical data, that because for machine learning, it can only take numerical data, that so this is for some string type. Okay, then you can do label encoder, okay, to automatically do it for us. Then we do the split. So this is as usual, nothing different. And then what next? If you take a look in this example, we use logistic regression. We also will consider decision tree. And what is the next one is KNN. And if you recall, we also learned the pipeline. So the pipeline streamline is, it can take care of feature scaling, and then dimensionality reduction, and then do model training. So we don't need to step by step. You can streamline them in a pipeline. That's what we learned previously. And we also learned the cross validation, like the k-fold cross validation, okay? So that's just all of those we already learned. So here we have these three different classifiers: classifier 1, classifier 2, and classifier 3, And for logistic and the KNN, and we, for logistic, we also have the regularization parameter, for nearest neighbor search, you can also specify the number of neighbors, for decision tree, how deep the tree is, and the criteria, the entropy, so that's, you can specify. And then with the classify, And for some of them, we also want to do the feature scaling. Is it? So for the first one and for the second, for decision tree and the random forest, we don't need to worry about the feature scaling. Is it? But for logistic regression and the KNN, because it involves the distance calculation, so that's why we also want to do the feature scaling. Okay, so that's why here we use pipeline. And we don't need to worry about dimension feature space reductions, because for the iris, there are not a lot of features. If you recall, for our handwritten digits, and we can use dimensionality reduction because that expedite. But for iris itself, the data set doesn't have so many features. Is it because for that one, the initial feature is 784? Is it because it's 28 by 28 pixels? Is it? For iris, I remember it's just 4 features. So different data set, they have different number of features. Then based on that, then you can make a decision if you want to do like the PCA, that principal component analysis, to reduce the number of features. And of course, decision tree can also do the feature importance to pick. Okay, and then next, let's see. So over here, for each of the classifier, we also provide them labels, okay, so that we can do some output more easily. And then what the next ones over here, we have three different classifier, and here we have the labels. Is it? A label is also a list, so you have 2 lists, and then if you record the Python, you can zip them. Is it? To have the tuples be generate a pair. Okay, so we make a full use of that, and then we can also do the loop. Is it? Do the loop, and then for each of it, then we do the cross validation k-fold. Is it? For the k-fold, then you can specify the training model. Is it? So basically, in this case, you are going to have 3 iterations. And for each iteration, you are going to do 1 classifier training. Is it 1 classifier training? Okay, and the fold is 10. And also, if you take a look for the cross-validation score, is it? You can also specify the score. Here it's not accuracy, is it? So we are going to collect the ROC, AUC data. Okay, but if you want to classify ROC and AUC, you must have that prediction probability available. Otherwise, you cannot collect this data. Okay, you must have that available. And then we can also calculate each of its mean standard deviation. Okay. And here is the output result, is it, for each one of it. So we can see each one of it, the result is not that great. Is it some just 85%-ish? Okay. So that's regarding this the first part, but not involving with any of the our ensemble learning yet. Okay. So next, let's see. we are going to make your use of the ensemble learning. Is it? With the ensemble learning here, we call the home-crafted majority vote classifier. And if you recall, and if we take a close look, what is the parameter it takes? It takes all three classifiers. Is it? All three classifiers. Okay, and for the all three classifiers, and then, so this is our majority voting one. Okay, majority voting one. And then we are going to add the majority voting one as it to our previous three one. We want to do some comparison. Okay, so we are going to have this new list of classifier. So the previous single three and plus the ensemble one. And same thing for the label, as it. And then we do the same loop, as it, and we pair. So this is, you are going to pair each individual classifier and its label. And then for each of it, we are going to do the training using K-fold. Okay, and then we can find the result. If you take a look at the result, it improves tremendously, is it? So it's get to 98%, because for each one of it, it's just 85, 87, and 92 at most. But this one, you can clearly see it improves a lot. Okay, and then what next one is, because over here, the accuracy, the scoring is that ROC, AUC, so we can do the plotting with the collected ROC and AUC. That how do we do it is, then we can predict, use our training model that we fit, and we predict the probability that with testing data. Okay, so we train the model and then we predict with the testing model. Okay, or with the testing data set. Then you just call that ROC curve. Okay, with the testing data. Okay, with the testing, then you can collect the false positive rate, true positive rate, and the threshold. And then we can also, with the true positive and the false positive, then we can find the AUC also. And then we can do the plot. And for the plot, and here we have the three different ones, is it? And the last one is the majority one, is it? The AUC, okay. So clearly with this ROC, AUC plotting, we can also see the majority voting one, is it? The area under it is the most, is it? So it's the best model, okay. So this is regarding the majority voting from this example one, okay. And for, let's see. For sklearn, okay, sklearn also has the ensemble learning, and you can use it's called voting classifier. Okay, so for this voting classifier, if you want to use, you first construct a list of classifier. Okay, so here we create an empty list, then we just call Python's append. Then we add one by one of the method. So it needs a tuple, okay, the classifier name and the classifier, okay. Then you just plug in this list of classifier to the voting classifier, okay. And then we can collect the score, okay, collecting the score. And here for the score, we still use the cross validation, okay. And over here, this is that ensemble 1, okay. And we do with the, you plug in with the training data, etc. And here is a k-fold, okay, it's a 10-fold. And for the k, you can also use the make selection k-fold, okay, and specify. And then this score is just the accuracy, okay. This is about the accuracy score, okay. So it looks like it's compared with this AUC, that AUC is about almost 98%, okay. Okay, so for this one, then over here, it also shows with the training and the score, ensemble score. And this majority voting ensemble 1, you can also call its get parameter function. With get parameter function, then it will give you each classifier and the related information. Because over here, you can clearly see you can also get even the hyperparameter information you will get it. Is it the hyperparameter? So you can get a parameter, you can get very detailed information about each of the classifier and their related information. You can see like the maximum number of iterations, is it? And the penalty, is it L2 regularization, is it? And for the decision tree, is it the ultrafilter use and the depth of the tree, is it? And even including the impurity related data, you can also classify, or you can also collect that, okay? And then for KNN, it's the same. So you can get a lot of detailed information, okay? And so today we didn't get a chance to complete study